Hello, welcome to the 12th session of this course. So here we'll discuss more about power series. Let's start with the power series. Uh, so what we'll present today is of course it's more about power series, but it's a convergence lemma by Abel. So suppose summation n z minus a to the power n from 0 to infinity is a power series in complex variable series in complex variable with of course the coefficients an in C for all n a belongs to C. Assume further that mod an z to the power n less or equal to so not z just it's z minus a, so z minus a to the power n is less or equal to m. Is it true? Yeah. Well, it's not exactly true, so not exactly the assumption I want to take. This is, suppose that there exist r greater than 0 such that I just explained after this statement why you need this assumption, such that mod of an r to the power n less or equal to m for all n natural number, then the series converges, series this one, summation n from 0 to infinity n z minus a power n converges absolutely and uniformly on the a row closure for all row less than r. Alright? So what it means is each of the terms, suppose each of the term is less than m. Of course you can remove finitely many if you want, that's not a big deal. So what does it mean? It means this would come in a construction of a geometric series, and that's why this is important. This is important to compare something. So this is important what? So this is what? Explanation is, so summation n r to the power n less or equal to m rho by what should I do? Yeah, so write it here, rho to the power n. So here rho by r. Yeah, see, yeah. So this is the explanation. Mod n rho by r to the power n r to the power n, right? And this is equal to m rho by r. So this is actually, this simple calculation is explanation for the condition here, the condition 1. You see, now we put summation this side, so this, you can compare this series with series summation n rho to the power n with this, and this is a geometric series with rho by r which is less than 1, and hence we have the convergence this side. So convergence this side. This is it. So let me write the proof. So if Z belongs to D A rho bar, this implies mod of Z minus A less than equal to rho. Alright? Now this implies mod A n mod Z minus A or n less or equal to mod A n rho to the power n because of this one. Alright, now we apply this. This implies 2 volts. This exponential volt. So this implies summation mod A n Z minus A to the power n, well, converges. Absolutely and uniformly on the rho cruiser. So this is by comparison test or Weierstrass-Emmett test. By comparison test. By comparison test, this converges uniformly as the series summation mn rho by r n converges, and that's because rho is less than r, implies rho by r less than 1. Right? This gives a proof. So this line, what is important in the whole proof, what you need to do is this one. You have to, what you need to remember in the proof, that you have to compare the series with the geometric series. And how do you get the geometric series with this way? Other things are nonsense writing. Of course, it's important for mathematics to write these things up, but the main idea lies here. Alright, so this gives so What does this give? Let me just erase this and write few corollaries. Alright, few corollaries. So if a series converges at a point, that means this holds for some r. Alright? If the series in z minus a in converges at z equal to b, so suppose z is a point here and so this is a is a point here and you have some point, let's say this is b, where the series converges. Alright? So then what do you get? You get a disk. So what is the distance? Mod of a minus b. Right? So converges at b, this implies mod of a in b minus a in converges to 0 as n tends to infinity. This implies there exists n such that greater than 0, such that this holds mod a in mod b minus a power n less than m for all m in n. Alright, now this implies by Abel's lemma the series n z minus a power n from 0 to infinity converges uniformly and absolutely on b a row closure where rho is less than mod b minus a, which is just a minus b. Alright, so this is an interesting corollary. If a sparse series converges at one point, so write this one as assumed, because assume, and this conclusion. This is a conclusion. The series converges in a disk. Alright? This is a very interesting corollary. Okay, so any other corollary you want to talk about? And of course, the theorem holds in. This is just one corollary only, and this is lemma. The theorem lemma holds in for pause series in real one variable also. Real one variable. Alright, so this is end of this session. We'll look more about power series in the next session. Thank you.